Okay, so yeah. So what's open one again? Something about argon and a lighter
Yeah.
atom thing.
How is it possible for a much heavier atom such as argon, with an
Yeah.
atomic weight of 39.95 grams per mole, to have the same energy as a light atom like helium, with an atomic weight of 4 grams per mole?
Hmm. Um. I mean, I would just say if it has a higher temperature.
Okay.
I mean, I don't. So I mean,
Uh-huh.
I guess. So if we let's just pretend we need to think about this,
Mhm.
even though I think it's just it's
Yeah.
hotter. But
Yeah.
anyway, so it's a hydrogen or helium? Hydrogen?
It's argon, the heavier one,
Yeah.
and helium is the lighter
Oh,
one.
helium. Okay.
Yeah.
So yeah. So I guess what they're asking is, they're asking something about how can they have the same energy when
Yeah.
this one's much heavier. I mean, if you actually compute the actual literal micro values of the energy, you have
Mhm.
this plus, I mean, obviously it's going to be, let's just do in one dimension for now. Of course, there's y and z dimensions too, but the energy is going to look like this. Now, m
Yeah.
is the mass
Yeah.
of each of the atoms. So of course, for argon, it's going to be much heavier. So m argon, I guess I should use the symbol, is much greater than m of helium. But of course, if they have the same energy, well, that's fine. You just have to make v bigger.
Oh, okay.
Right, like it's, what I mean? Like the energy is not just the mass, it's the mass times this
Yeah.
in all the dimensions.
Okay.
So if we just want the energy to be the same, we could just say, well, the helium has to be moving faster, which is kind of a silly thing to say. Now, it seems like we're just talking about one atom here,
Mhm.
which is fine because we can, but we know that, like, when we talk about thermodynamic quantities, we're actually taking the average speed and the average energy of all these things. So this just means that the helium is hotter, right?
Yeah.
Well, actually, okay, maybe it's not hotter. Because if it was the same energy, I guess it's the same average energy, so it's the same temperature. So I guess it's not hotter, but it's moving much faster. So that's it. Though I guess the whole thing is, how can these have the same energy when the masses are different? Well, the V can be different. So,
Okay.
so given a fixed average kinetic energy of some atoms,
Yeah.
The argon, the heavier one, will be moving much slower. So that's kind of the whole thing.
Okay. And these are
Kind of
just
a weird
atoms, so yeah, it'll just be kinetic energy, not the rotation.
Exactly right. That's why I was
Yeah.
wondering if it was hydrogen or helium,
Yeah,
because argon is just a single point
Yeah.
nucleus, and then,
Yeah.
whatever, and so is helium. It's just obviously smaller, or whatever, or lighter.
Right.
But they don't have any rotational energy, and they don't have any, vibrational or anything like that. They're just,
Right.
they're noble gases, so they just have one.
Okay.
Yeah, so that's kind of the whole.
Doesn't moving faster mean higher temperature?
No, not exactly, because the temperature is like the average kinetic energy, and the kinetic energy is mv squared. So
Okay.
even if v is bigger, there's still the m there.
Right.
So if they have the same, if you're saying that they have the same average energy, you're already, before you even think about any of this,
Right.
you're already saying they have the same temperature.
Okay.
Yeah, I literally just made the mistake a second ago, because
Yeah.
you see it, you'd think moving faster would mean higher temperature, but
Right.
if they're telling you their energy is the same, then by definition their temperature is the same. We just know that the temperature of let's just say like a hot heavy gas is moving like slower, right, than hot light gas. It's just the statement that if this quantity and if the average value of this is constant and m is larger in one case, v must be smaller, right?
Right.
So yeah, you'd get that the temperature, right, of these. If you have a very hot sample of argon, you might not actually get them moving as quickly.
Okay.
Anyway.
All right, that's...
Yeah, so that's kind of a sort of
Yeah.
qualitative type
Yeah.
question.
I think the next one is pretty... Yeah. Where did the energy stored in oil and coal come from originally? Discuss the process. That's
yes.
pretty subjective.
Yeah.
Yeah.
So yeah, oil and coal are, of course. I don't
Yeah.
know what this has to do with
Yeah.
thermodynamics yet, but
Yeah.
that's obviously very qualitative.
Yeah.
It just comes from the sun, of course. It's all just dead
Right.
plants, so they're
Uh-huh.
absorbed, and
Right.
I mean, I could just, I guess, talk about. I'm sure most people know about how. I don't know why I'm even drawing the molecule, but if you just have CO2, so plants take in CO2. This is like obviously like first grade or whatever, but they take in CO2 and they turn them into like the actual material they're made of, and sugars and other, so like complex molecules. Because if you want to make a tree or something, you have to kind of make a complex molecule to make it stand up. And you also, or if you want to make fruit or whatever, the tree, however that works, or I don't know why there's, anyway, whatever. The point is you have to make complex molecules, and the only source of carbon is really from CO2 in the atmosphere. Plants are in the ground, but the ground doesn't actually provide with that much carbon. It's actually pretty much just the air. So it's the CO2 in the air, of course. Does this, and how does this work? This takes energy to do pretty much anything. Well, not everything. Some, what do they call it? Reactions give you up energy. Yeah, right. But this one takes energy. This is the sun gives energy to do this, because it's not sort of easy to break this apart and construct these things. So of course the sun gives us energy. So this has more potential energy. We know it has more potential energy because energy went into it and didn't come out anywhere. Right. So just the fact that there's these big molecules is more potential energy. Then they get buried, the trees and the other plants and whatever it is gets buried in the ground for a long time, and they decay. And of course, the energy doesn't go anywhere. It just sort of decays into, decay meaning breaks apart into different amounts. But it's those molecules are still very complex, and then from those you can get like oil, or basically like coal, just things that are like a carbon and then a bunch of like hydrogen on them. What are they called? Polycarbons, or I don't know, whatever they're called. Like
hydrocarbons.
Hydrocarbons. That's what I was thinking of. Yes, you get like hydrocarbons, which are literally just like things how you make plants and all this stuff, but they've somehow, for whatever reason, given up their oxygen. I don't know how any of this works really. I just somehow you get things like this and this. This is all hydrogen here, and there's carbons here. Well, if you light this with a flame, it very often will want to turn back into. We knew that it cost energy to get it to here, so to get it back must give us energy, and that's literally the energy we get from this. So
so when it says discuss the process, is this what we are writing about?
Yeah, you can. I mean, I don't know if you really have to say what the things are. I mean, essentially, there's one process of what the plants are actually doing.
Okay.
And then there's another process, because the plants don't actually make, like propane or whatever this is, right? Like they don't literally make propane and stuff, but the decay underground for a million years or whatever, I don't know why, but it somehow gives you propane and that kind of stuff, and higher order hydrocarbons. And the big giant ones are sort of more, they have much more like ability to stick together. So they tend to be more solid, or more at least like dense liquid. So those are like coal and oil. And then if they're very light, like methane, which is just this tends not to want to stick together, because it's sort of small, and the electrons are kind of distributed around here. So this is like a gas, and that's like natural gas and stuff. Anyway, so depending on how big they are, they can make different solid, liquid, gas, and that's just natural gas, oil, coal, and all that stuff. So anyway, so that's all just random facts, but hopefully. So I don't think you don't need to like tell me exactly what's happening, but just the idea that the sun costs energy to take CO2 and turn it into something complex that has potential energy, and then now that there's something with potential energy, we can definitely use it to get the energy back.
Okay.
But of course, that ends up costing you, or not costing you, but giving up CO2 again, which is sort of turns out to be a downside. But anyway. Okay. Hopefully that's good.
Right. Yeah. Like, how do we answer this question about the Hurricane Sandy thing?
Oh, is this number 4?
Yeah.
Yeah, so it was like Hurricane Sandy, how much energy does it have? And
how is it stored and released? I believe it is from the sun.
Yeah, so it's from the sun. I mean, you could think of like there's the ocean,
Right.
and the sun gives energy to the ocean that makes it hot.
Yeah.
I mean, relatively hot, so it makes things evaporate. Um, and then, so I guess you have a bunch of water vapor in the atmosphere now, and because of like rotational motion of the Earth, you get like big swirling things. I mean, I have no idea how you'd say how much energy is in.
Yeah. How's it stored and released, and estimate the amount of energy stored and released by Hurricane Sandy in particular for some reason.
So I mean, there's like 1,000 ways you can answer this question,
Yeah.
and they are thinking about one way to answer, and I don't know what it is because I can't read their mind. So
Okay.
that's literally the crux of this
Okay.
question. I would say if you want one answer, it could be you could say, well, what's the I mean, I guess you could find the average wind speed of the hurricane, and then find how big it is, and just assume it's like how big it is, meaning I guess you'd need to find the volume. So you look up how big it is if it's a circle, right, or a disc. You could find the radius. I don't know, I have literally absolutely no idea what it would be, a couple hundred miles or something probably, but probably more than that. But anyway, and then somehow you could find the depth of it because it's sort of deep, and then anyway, and then you basically could say, well, there's that much air, and find the density of air. Look that up too,
Mm-hmm.
and then just say if that much air is moving, so the density of air times the volume would be the mass of the air. So you could find the total mass of the air in this sort of cylindrical region that you're saying the hurricane is.
Mhm.
So once you find this, so total mass of air is density times volume. Obviously, this is just what mass is, right? So density of air, you could look up. Volume, you could somehow compute, I guess. And then if you do this total mass, m, times the average velocity, and you do 1/2 mv squared, you'll get like the total energy.
Right. Okay.
So I just made that up. Of course, you could also, the only other way I was thinking you could possibly do something like this is like find the total amount of water vapor that's in it, and then find how much energy it takes to like evaporate. That's really beyond, I think, what we're at so far, because that involves like the energy due to the latent heat of vaporization. So all this stuff we haven't even talked about yet. So I assume you could do something like this. I mean, again, this is a question that you're going to have to work hard to get wrong.
Right.
When I grade them, I'm not going to mark you wrong unless you literally don't write anything. If you write something reasonable, I mean, this is just an example, but if you come up with another way to measure it, that's fine. Now, when they say something about, and this is going to be in joules, hopefully, if you do everything right. This is in meters per second. If this is in kilograms, so make sure you look up the mass of air in kilograms. Obviously, very small per cubic meter, whatever. This will be in joules, and then you can compare that if you look up the power usage of New York City or something. Yeah. So you can look that up in joules as well. Obviously, that's going to be in joules per second because it's, So you would just say, like, I guess how long do you have to run New York City for to power the hurricane for its entire life or whatever, right?
Yeah, that makes sense.
Oh, I guess so. Yeah. Okay. I guess that's fine. So you're finding the energy just in the hurricane at one moment when the speed is that speed. You're not finding like the total power output or something like that. Anyway, whatever, it doesn't matter. So this is just an example of what you could do, and then energy of a city would be obviously continuous in watts. So a watt is just a joule per second. So you could use that to compute the seconds if you wanted, or just compare them. Just say in a day how much. If you look up how much energy does New York City use in a day, you could compare that to this. So.
All right. So by this method, we are kind of approximating the funnel. I'm not sure if it's a funnel. We are approximating it as a cylinder or something like that. So.
Yeah, I'm making a giant approximation.
Okay.
So I'm assuming it's literally a cylinder, like a disc cylinder like that, and the entire thing is just moving at this speed. Now, of course, it's not like the center is, if it's going like this, the center is not moving at that speed, and the outside is, I guess, moving faster. I mean, actually, I don't know how it works. Maybe the middle is moving. The point is that they're all moving at different speeds. It would be really hard to actually compute the energy.
Yeah.
So if we just look up the average speed, it's probably 100 miles an hour or 50 miles an hour, I don't know, whatever.
Yeah.
You look it up and just just assume that you have this much air moving at that speed. Don't care where it's going,
Right.
what part is this. You'll get a rough approximation. I think this is his whole thing. At the beginning of the year, he kept talking about things in like powers of 10.
Mm-hmm.
Is it this many joules or is it,
Okay.
this many joules? Like these are very different numbers.
Right.
The number that you multiply by doesn't really matter too much. So I think this will get you within the sort of general realm.
Okay.
Anyway.
Okay. Yeah. This one's about equipartition theorem, the 7th one.
7, yeah. Okay.
I'm a little confused about the specific heat as well.
Yeah, sure.
Yeah.
So what is 7?
What would the equipartition theorem predict for the specific heat per mole for methane? CH4, and compare your prediction with room temperature specific heat at constant volume.
Okay, so all the C's we're going to do I think in the entire class is going to be at constant volume. So they say that, and it probably is a little bit worrying because you're like, wait a minute, I didn't think about volume.
Yeah.
That's just a convention. You can actually do like all of thermodynamics kind of thing with a C at constant pressure. That would be the alternative. But we're always going to do it at constant volume. Pretty much everyone does that anyway. So they're asking you to compute this for CH4, which is methane, which is, I kind of just drew it. It kind of looks like this, I guess.
Yeah.
I mean, it's in 3D.
It mentions its tetrahedral shape.
Yeah, it's a tetra. Right, exactly. Because they're so if you take this is like a math fact, but if you, take a point and you try to put 4 pegs on it that are equidistant all apart from each other, the angle between any 2 is the same. There's only one configuration, and it's like I can't even this and then this.
Yeah.
Anyway, it's hard to draw, but it's like if you draw its shape, it would be like 3 triangles, kind of like that. Anyway, whatever.
Okay.
So it's a tetrahedron. So I'm just drawing it like this for now. But we know, what do we know about it? Well, we know, we have to draw it first.
Okay.
So let me draw it a little more carefully, or a little bigger. So let's just pretend we have these 4 things in the flat plane. But we have to keep in mind that it's 3-dimensional, and it's kind of like a pyramid, I guess. If you put one at the top, they'll make a triangle at the bottom.
Yeah.
So now, to find out let's look. So the equipartition theorem literally says that each degree of freedom gives you an energy value. It contributes to the average energy this much, 1/2 kT, where K is just a constant, T is of course the temperature. Now C is the derivative of the energy with respect to temperature. And usually they write as derivative of heat with respect to temperature. So sometimes they'll write Q kT. Now Q is just this. It's because it's the energy due to temperature. That's all they mean by. It's just that sometimes it's helpful to talk about heat because you're adding or losing heat, as opposed to work is the other form of energy you could do. So I'm going to erase this for now, but just remember that that this is C is this, and so if we take the derivatives of this, we'll get C for let's leave this for now. Because I don't want to take a derivative yet, because this is not actually we actually want to find E. That's what we want to do. We want to find E in terms of KT with a number here for methane.
Right.
Right? Now, that's what we need to plug in here, and then we can look at this for now, right?
Okay.
So, so this is going to be, this rubber is for 1 molecule. This is the energy for 1 molecule. Each degree of freedom it has gives you 1/2 kT. So this number up here is going to be the number of degrees of freedom, basically. So now the problem is just how many degrees of freedom, I'm going to use DOF for degrees of freedom, does methane have? Well, we know it has, so it's moving in 3 dimensions. We know it has at least 3 because it can move in 3 dimensions, the whole thing. So we have, I'll write it as, I'll just write it as Vx, Vy, Vz. I'm not going to write, you could write, I guess, 1/2 mv squared, 1/2 m, but it's these 3. What else do we have? Well, the other two types were there was rotation and then there was vibration. So
yeah.
right, so let's talk about rotation. Well, it's a tetrahedron, so I guess I probably shouldn't have drawn it like that, even though there's sort of no other way to. So it's like that. Well, sorry. Let me. There. So the points of the tetrahedron are hydrogen. The center is carbon. I haven't drawn the center because
Right.
it's just going to mess it up. But
Mhm.
this is the symmetry of it, right? So in this one, well, we could definitely, if we put an axis like this, we could definitely rotate it like that, right? Because there's points away from. The only reason we couldn't rotate around some axis is if everything was lined up along the axis.
Right.
But of course, we can rotate like that.
Yeah.
But then if you look, well, what about rotation through this axis, like that way? Well, that's also fine. And then you could also think, what about rotation through this axis, like that? That would also work. And so we know that there's, I'll call it x. I'll just pretend this is x, and now these are not actually y and z,
Right.
but I'll call them y and z. Now I guess I probably shouldn't have drawn them like this because this makes it look like, well, there's 4 points, so it seems like there's 4 axes I could rotate around.
Mhm.
But in fact, if you try to put an axis through this 4th point, you'll find that it's just a combination of rotation around these 3. Like if you rotate, it's really hard to visualize, but if you imagine like every object,
Mhm.
no matter how many points or whatever it has, can only do, I should go in front of the camera. This is one, right? This is another,
Right.
and this is the third.
Right.
You literally just, it's kind of like saying you could move in a 4th dimension. Of course you can't. You could make up another, you could be like, what if I pick these 3 directions and then this direction? It's like, well, no, that's actually a combination of the other 3. So in this one, I'm just using these as examples because there's points, so you might as well put lines through them, just to make it easier to imagine what's happening. But you can never ever have more than 3 rotational.
So does
degrees
that
of
mean
freedom.
these are orthogonal? These axes?
These axes are not orthogonal. That's
Okay.
why. Yeah, if they were orthogonal, it would be obvious that I couldn't make any more because there's only 3 orthogonal things, right?
Yeah.
So these are not orthogonal, and in fact, that's why it looks like a 4th one would work because they're not orthogonal.
Right.
So I shouldn't really be drawing them like that. That's why I said they're not really y and z. They're actually like, it's like if this is x, well, I should be like, I guess I should call this z, but these two are actually a combination of all 3 axes. So this is like, this one is kind of like a combination of x, y, and z in some proportion, and this is like, x minus y and z, and then the other one would be like minus x, y, something like that. So, sorry, this literally is only just for confusion. If I really wanted to be, if I wanted to be more helpful, let's try to be more helpful. How about this is one axis, this is another one, and then this is the 3rd one.
Right.
It's just that then those don't go around, like none of the points are fixed around this axis, but then it's clear that there's clearly no other ones I could draw.
Yeah.
And just because I squished the axes somewhere else doesn't mean I can magically make a 4th one. There's only 3 because of it's in 3D, just like there's only 3 of these because it's 3D. So basically,
Probably we could consider the center of mass of that tetrahedron or something, for the origin to be at the center of mass. And
yes, these are all around. That's a good point. Around center of mass.
Right.
Yes. So you could. I guess you could think about rotations around other points, but it always will work if you always consider the center of mass. Yeah. So I haven't even drawn it, but I guess that's a good point. That you should put the origin at the center of mass. Yeah.
Right.
Anyway, so there's 3, and we know there's 3 because there's no sort of I'm trying to think of an example besides this one where it's a line. Where this one now only has 2 moments of inertia because it's just like a marker, right? Where this one doesn't count because now this is actually, of course, thick, but like if it was infinitely thin, this wouldn't mean anything.
Right.
You could have this and you could have this. I guess that's it, right? There's no other. That would have two rotational degrees of freedom. Every object that spans all three dimensions. I'm just trying to think. Wait, what if it was like a plate? You had some like this. I mean, you could spin it like this, and you could flip it like this, and you could. Well, yeah, okay, you could flip it all three. Anyway, I guess you can have it all three. So, yeah. Okay, so then we have three rotational ones, but we don't just have these, because remember, now this is why I drew this one, even though this is not really accurate anymore. You could still vibrate these things right here, and the thing is, I'm not sure, because it seems like then there'd be four, but there might be some special symmetry relations. This is actually probably too hard. In terms of like, maybe they don't even want you to think about this. I'm thinking maybe they want you to say the answer is 6.
Okay.
Because these vibrations are actually, in real life, these are really complicated because like, it's not just like there's 4 independent springs. It's like they're coupled in such a way where like, vibrating one actually does vibrate all of them, and how many different modes can you vibrate them in? Like, you could think of the carbon as like going this way or going this way, but like in the 3-dimensional picture, how many ways can you do that? I mean, it looks like the answer is like maybe 3, maybe 4, because there's 4
bonds.
There's 4 bonds, so. But of course, oscillating in one bond actually has to oscillate all the other ones because they're connected. So like, how many are there? I think they want you to say 6, and they want you to, because the only time they talk about this in the slides is for a lattice.
Right.
So it's probably 6, but let me look at the solutions because I just want to see if they want you to like, if there's some special trick. Yeah, because I imagine. Okay, and the solution is called assignment 4. Well, actually, you can't see it anyway, so. And this is 12.4.
12.4. Oh, I'm sorry.
Oh, 7.
7.
Yeah. Vibrational. Oh, there's a formula. Sorry. I guess it wasn't in the slides. That's weird. Yeah, I recall this formula. So there's a formula for vibrational, and we did not talk about it, so I don't know where. It wasn't anywhere. That's very strange. But there's a formula, and it's this, and I can't remember where it's from.
Okay.
Where N is the number of molecules.
Okay.
Number of atoms. Yeah. So in this case, how many atoms are there? There's 1, 2, 3, 4, 5.
Yeah. So 9.
Does that make sense? Oh yeah. So I guess it would be 9. So this would be 3 times 5. So 15 minus 6 is 9. So I guess we have then 9.
Okay.
Okay, that's what the solutions say.
So it's probably
Okay.
the 3 linear motion, 3 the rotational,
Yeah.
and 3 from the vibrations.
No, it should be, it says 9 from the vibrations.
Oh,
Like,
okay.
this is just for 9. Yeah.
Vibrations. Okay.
This is just for vibrations, I mean, yeah.
Okay.
So now I don't know for sure. If it's in the book somewhere, then maybe you're supposed to use this.
Okay.
But I'm not sure. And then it says, so I'm just kind of reading from the answer. It says at room temperature, the total degrees of freedom is 6. Okay, it's even more confusing. So remember that chart where if it was a function of temperature, you had this thing where you had this was linear motion, this was linear plus rotational, and this was linear plus rotational plus
Oh yeah.
vibrational. Now that just is telling you that these are the easiest to excite. This is the thing with the buckets that I was trying to
Right.
say. These are the easiest to excite. These are a little harder to excite, and these are much harder to excite. But if I get to like really, really high energies, eventually I'm going so fast that like they're basically all they're all equally easy to excite because I've gotten to the part where it's sort of hard to excite all of them in the same way. So now it's sort of, so the statement in the solutions, it says at room temperature, total degrees of freedom is 6. So somehow, so this is where I should have just read the book probably, because somewhere in the book, apparently, it probably has some formula that tells you for different molecules what temperature you need to be at before. So it's claiming in the solutions that the total degrees of freedom is 6, which means only these two are excited, which means that it says at room temperature, so at room temperature, which is like 300 Kelvin or so, that you're here. Now, this chart is just a made-up chart that was in the things. It doesn't actually tell you any numbers, but I assume somewhere you could look up what, for a certain molecule, when does it do this thing, right?
Right.
So all of that's just my predictions.
Okay.
I would say the important thing is if you understand all of this, it's fine. The reason it seems complicated is because of my lack of understanding of what the book says. Okay. And also it's not in his slides. So that's why I'm a little suspicious of this, is that it's not in his slides anywhere. This formula is not in the slides anywhere, which is kind of weird. I do remember this from like when I took chemistry, but we didn't really use it for anything. But I mean, we used it to compute things like this. But anyway, so apparently at room temperature, you're only supposed to consider these first 6 excited ones from some table, I assume. There's a bunch of I don't know. I've asked them to give me a book, and they said sure, and then they never gave me one. So I don't know. So I will at some point figure out how exactly you're supposed to know that these are not excited, other than the fact that you should know in general that these have a higher temperature to be excited, and these have a middle temperature, and these are the lowest. But for a specific temperature that they're giving you, room temperature, I think technically they say 295, but whatever, same thing. Okay. It's like 25 Celsius, which is like 70 something Fahrenheit. So anyway, so apparently the answer is 6 degrees of freedom. So when we get this, so this is the energy of a molecule of methane as a function, in these terms, right? We could of course write it in terms of these things too, but we don't want to do that. And now we want to actually find the specific heat per mole. That's the actual question. So now we can take the derivative with respect to T, and we would get, 6/2 is just 3 times Kb. Yeah. And then this is the specific heat. This is C per atom, right? That's sort of how we got this. This formula is per atom, right? Atom. And now if we want to take C per atom, we have to multiply this by n Avogadro atoms per mole, and then we will get C per mole. Right, does that make sense? So this is just all I'm doing is converting units from atoms to moles, right? It's just that it just happens to be a nice number with a name. But this is just the number of atoms in a mole, which is, Okay. So C per atom is 3 Kb. So to get this, we would get C per mole is 3 Kb Na. And that's it. So that is C. That's it. And of course, these numbers end up being, they're called R, the gas constant or something. Okay. So it's like 3 or 8 or something. Okay. But it doesn't have any powers of 10, which is kind of interesting. Right. Because these kind of cancel out roughly. This is like 10 to the minus 23rd, and so anyway, it's like 3 times that gas constant, which is kind of obviously you can kind of see now why the gas constant is so nice.
So what does the specific heat actually mean, like physically? I'm still not.
Yeah. So physically, it means this, which now maybe that doesn't help because it's still an equation. So what it means is that like, I think of it. This is how I think of it. It's kind of like the inertia of changing the temperature. So if you give something a bunch of heat and its temperature changes just a little bit, it seems like it has a lot of inertia. Has a lot of like sometimes they actually call this thermal mass, right? That's actually specific heat per gram or something. But anyway, it's very basically similar. It's basically like how much resistance does an object have to changing its temperature. If you give something a ton of heat, if you put it on a flame for a while and it changes temperature just a little bit, it effectively has a big, like, it's very resistant to changing temperature. That would mean it has a very large specific heat.
Right.
Let me just make sure I said that right. Actually, maybe that means that, hold on. That means it has very low specific heat. Okay, let's start. The idea is that it's a measurement of how resistant something is for adding energy to actual change in temperature. So you can actually imagine the actual inertia analogy kind of makes sense because when we were talking about the argon before, the argon would move much slower, but so you might imagine that if you add more, well, actually it might be the same. It would just be that they move slower. Okay, never mind, that's not a bad example. But you might imagine a molecule where there's more places to put the energy would not exhibit as high of a it would not change its temperature as readily because it's putting the energy in more places. So it's sort of not filling up as much as if there were just a few places to put the energy, then it might heat up much faster.
Right.
Right. So
so in case argon is monoatomic, so there's just the motion, and the mass resists the motion over there in a way.
So the reason I started to say argon and then I changed my mind is because even though argon and helium, if you just imagine them in the same system, even though it seems like something's resisting in argon, something's resisting motion, right? It is resisting motion because it's heavier. So heating something up or raising its temperature or doing any of those things would cause them to not move as quickly, right? But their specific heat is actually the same. And the reason is because we don't actually care about the motion themselves, we care about the energy. And energy is like 1/2 mv squared for a molecule. So even if m is higher, and we're just saying that that if we raise the energy by a certain amount, well, m is higher, so v is just going to be lower, or whatever.
Right.
But all we care about is actually just the energy, which could be the same in both cases. And actually, in this case, we only care about the places to put the energy, right? If you can put the energy in argon and helium, you can still only put energy in these 3 places. You can't put it anywhere else.
Right.
So therefore, adding energy corresponds to the same sort of output, right? Because same output meaning the same measurement of temperature. So the thing I was confused by, which I'm still actually not positive on, is either one of them is a very high specific heat and one is a very low specific heat.
Okay.
The idea is that specific heat measures the resistance to temperature change when you put energy into a system. So if we put so let's say we put a lot of energy in, and we received a very small change in temperature, we would have a very large specific heat. Yes. Okay. Then that's true. So very low specific heat would mean that you turn it on. Imagine I was just going to say imagine like a pot full of water versus a pot with very little water. That would actually not technically be specific heat because you're supposed to divide by how much there is. That's why it's per mole.
Right.
So, but heat capacity is basically specific heat where you don't care about how much you have. You literally just say, if we have double or whatever, So the heat capacity of 2 liters of water is twice as high as the heat capacity of 1 liter of water. And that's heat capacity is just this times the mass.
Okay.
Basically, so it's kind of the same thing. I couldn't think of an example where I don't really know of 2 materials that the specific heat is higher. I'm just trying to think of an example where something heats up faster than water. We don't heat anything else up really on the stove. I mean, like
alcohol. I don't know.
Yeah, but you don't usually like boil a bunch of.
Yeah.
I'm just trying to think of like what's like if you set out something to thaw, like meat or whatever that's frozen, and you set it to thaw versus like a vegetable that you've frozen for some reason. I don't know why you've frozen. Well, you could have frozen that. Yeah, you could have anyway.
Yeah.
I mean, anyway, you can imagine that some of them respond quicker. They're getting the same amount of heat, but some of them don't melt because the temperature is, or thaw or whatever, because the temperature is not changing as much. So they have more sort of inertia. They have more sort of thermal resistivity, and that's this thing.
Okay.
So water actually has a very high specific heat compared to like most things, which just means it's very hard to change the temperature of water, which sounds like well, I guess you mean compared to what? But like compared to like the same mass of like a kilogram of water versus a kilogram of like steel. I'm pretty sure, I'm not positive, so don't quote me on this, but I'm pretty sure that water has a much higher specific heat than steel. Meaning heating up a kilogram of steel from 5 degrees Celsius to 10 degrees Celsius is much easier, will take less heat than heating up a kilogram of water, which is kind of weird. Like, it seems like, well, it's a liquid. It seems like it would be much easier, but for some reason, water, for various properties I don't understand, water has I guess you could think of the number of degrees of freedom. There's more vibrational ones because it's like a molecule. There's more, it's not like a symmetric molecule. It's like a diagonal, it's a V. So there's multiple rotation axes you can put, and then there's some vibrational. So I guess you could imagine that there's more degrees of freedom. So
I vaguely remember that there were some van der Waals forces as well in water, I believe.
Yes.
Yeah, that caused the boiling point to be higher than.
Yes. So there's like those are like intermolecular forces, right? So why is it a liquid at all? Why is it not a gas? Well, there's some forces, of course, keeping them together. Exactly.
Right.
And so, and because of the properties, water versus methane. I don't know the van der Waals versus methane, but I assume it's lower. Maybe because there's more sort of symmetry. Like I know there's stuff about like how water molecules, like there's sort of it's like they're like polar, right? This is like the plus side. No, this is the minus side. This is the plus side. I don't remember. One or the other. One side is plus, one side is minus, and that leads to more like hydrogen type bonds or like just bonds between molecules, and that leads to them sticking together. And so, yes, it might be like those bonds are more places that potential energy exists. Therefore, when you put in energy, it's going into like loosening those bonds as opposed to raising the temperature. Right. So it's sort of again, it's just more places to put the energy that's not just raising the temperature.
Okay.
Yeah.
So does thermodynamic, the degrees of freedom, does it consider that as well, that intermolecular things?
It would if we were being accurate, yes.
Okay.
In this counting that we're doing, we're approximating everything as like a gas with weird molecule shapes. Right. Like we're considering things that are weird shaped, considering things that are not symmetric. This is always true, of course. So we're considering things, but we're not considering intermolecular forces anywhere in here. So you saw from the table that, of course, the numbers are not literally 6 or 3, I guess, and 1.5. Or some of them were pretty close. The gases were pretty close. Right. But once you get into liquids and solids, you get into exactly what you were talking about, intermolecular forces, where now you're literally not even considering that here.
Right.
So you're sort of definitely going to get it wrong a little bit, and depending on how much molecular forces or if it's polar or if it's not polar, you might get it wrong different amounts. So I would just guess based on this that methane, if we did all this and we actually measured it for methane, it would be more accurate than for water.
Right.
Because with methane, it's obviously a gas, so therefore there's less intermolecular forces than water, which is a liquid at room temperature. So anyway.
So I'm not yet sure like how it's 6 because we are just considering the linear motion and the rotational motion, but not the lattice vibrations. Okay, that's probably dependent on the chart.
Yes, and so the thing that is sort of bothering me a little bit is that in the slides he only talked about vibrational in the sense of lattice vibrations, which is true as well.
Yeah.
But then you don't have this formula because in a lattice, like there's no like how many atoms are in a lattice, there's a bunch. Right. So you don't have this. this vibrational is the real, is in this chart, this is what he's talking about. This is all for a gas, right?
Right.
So this is, I guess it could be for a liquid too, because I guess it could be for a liquid, but of course then we get into the problem of intermolecular forces. The whole reason liquids exist is because of intermolecular forces. So let's just assume it's a gas. There is he admitted in a sense the slides I should say admitted that there's a vibrational component to the gas, and it's given by this formula according to the solutions. But he didn't mention it anywhere, and he only talked about vibrational in the sense of lattices. So I think what you're just supposed to know is that this exists. It really does happen at high temperatures, but for everything that's at room temperature, you can kind of ignore it because it doesn't really happen until you get to really high temperatures. And we do need to know about vibrations because lattices have them even at low temperatures. So solids that are crystals like lattices or glasses or anything like that, it's not this formula, it's just another, you just have to count or whatever. But it really does have a vibrational degree of freedom at all temperatures, because in a lattice, that's essentially like motion. Like in a lattice, you can't have even motion without having like a spring compression, right? In a solid, right? In a solid, to have any kind of motion involves compressing a spring.
Right.
So you have to have both of these they kind of go together in lattices, so you don't have the same chart for a lattice. But anyway, okay. I think those are the main lessons he wants you to know.
Okay.
Yeah.
Okay, this one is a long one. The 11th one talks about Fermi spheres. So the second part, like right down there, the second paragraph is mainly the question, I believe.
Okay.
Yeah. A metal with Fermi energy 5 electron volts. Find the volume of K space with less than Kf. Okay. Convert this to a density per cubic meter of electron states. Assuming there are 2 electron states. Well, I'm not sure what this is asking.
Let me look.
Oh,
wow. That is... Okay. Uh-huh. Okay. Oh, I see. Okay. So I'll do my best. So is that right? So what was it's in the first paragraph they have an equation.
Yeah.
Over H.
Yeah.
H bar, I see, okay.
H bar, yeah.
Okay. So they give you this formula. Now this formula is just the same as right. So this is just energy is p squared over 2m. That's just always true. But then p, in when we're talking about Fermi energies and stuff, we always want to use k instead of p, which is just h bar k. So if we substitute that, we get this, and we solve for E, and we get this. Now, if you just put F's there, that just tells you you're at the Fermi level, Fermi energy, and stuff like that. What they're asking about is if you have a material with a Fermi energy of 5 electron volts, then they want you to find the volume of K space with K less than Kf. So, okay. So what they're asking is if you have Kx, Ky, that's Kc like that. So so remember when we have the actual wave function for these electrons, it's like e to the ikx times the periodic function. Yeah. It's just in a lattice or whatever, in a metal, for example. Then they really have 3 components, x, y, and z. And what they want you to do is find, what they're saying is that electrons seem like they should behave like they're in a gas or something when they're in a metal. So why don't they have like 3 halves kT? That's the whole premise of the question. Mm-hmm. And the answer is because that they kind of tell you is that if I draw this as like a sphere where the lowest energy states are in the center, and then so this is 2 electrons, and the next state is like here right next to it, which is also 2 electrons. Because it's in 3-dimensional K space, it actually fills up like a sphere, right? Because the farther away you get, the more energy you have, because the energy is proportional to K squared, right? And so K squared is the distance from the center. So it fills up like a sphere, right? It's the same as, remember, we have this E versus, so there's no E here. Just keep that in mind. There's no E in this plot. But if we do the E versus K graph, we have the bands. We start at the bottom and start filling them up. This region is a sphere. Mm-hmm. It's just in 1 dimension, so it's a line. But I shouldn't put a circle around. I really should put a line there, because remember, so a line is a sphere in 1 dimension, and this is E is like K squared, right? That's just that formula there again. And let's just say that the Fermi energy is here. Therefore, we get the Fermi momentum is here. We can compute it because this is a parabola. This is just this parabola. We can just compute it with this formula, and we get that. Then we get that this line here, I mean, it's just, it doesn't matter where it is. It's just the line that goes from here to here, this to this, is the Fermi sphere, where this is minus Kf and this is Kf. Right? Does that make sense? It's very strange now that I'm calling this a sphere. Mm-hmm. But it is a 1-dimensional sphere because we had a 1-dimensional thing. So this is just the bands from last week or whatever, or yesterday, whenever we talked about it. But we did all of those in 1 dimension because we had a 1-dimensional lattice and stuff. So therefore, we get a 1-dimensional region where the electrons all exist in, and that's called the Fermi sphere. Now, when we go to 3 dimensions, it's exactly the same. Each axis is its own little thing like this. Of course, now I can't put energy anywhere because there's no other dimension. Yeah. Exactly. But they fill up inside a sphere, and the radius of this sphere is going to be the Fermi momentum, and you could compute the Fermi. The Fermi energy is kind of like a measure of how big it is. Obviously, if you increase the Fermi energy, you're going to have to, well, that's not really how you do it. I guess if you want to say, if you add more electrons and you increase the Fermi momentum, the Fermi energy will automatically change because it's just Kf squared times some constant. So this is now the Fermi sphere in 3D. Okay, and this is still solutions to this thing. It's just now let me write it like this. It's now x is a vector where x is actually x, y, z, right? I k vector dot x vector of u of x vector, where x vector is actually x, y, z, because it's in 3 dimensions. I probably shouldn't use x, but I'm just going to keep using it. Probably should use r actually, but anyway, whatever. So this k vector is now here. It's any vector in here, and the components are x, y, and z, and the radius of this is the radius of the Fermi sphere in 3D. So when they want you to find the volume of K space, that with K less than Kf, they're just asking you to find the volume of a sphere with radius Kf, right? Because the radius of this is Kf. So what is the volume of a sphere with a radius Kf? Well, it's 4/3 pi r cubed, right? It's the volume of the sphere in 3D. And r is now Kf. So we get this. But of course, we want to express it in terms of the energy we're given. So we'll plug that in. So this is actually 4/3 pi. This cubes, this is going to be, well, it's going to be h bar cubed on the bottom and 2m EF to the 3/2 on top. So this is the volume of the Fermi sphere. This is this thing. The volume of the Fermi sphere with K less than Kf. Of course, K less than Kf just means the volume of all of the occupied things. Occupied electrons, I guess. Now, if we wanted to now say what's the density per meter cube, well, now we're talking about, so meters cubed is real space. It's not K space. Mm-hmm. So this is not in real space or anything. Right. But they say that, sorry, can I look at it one more time? They say something about the range of, yes, 2 electrons. Okay, so for each, then we have to say for each 2 pi cubed volume in K space, there are 2 electrons. Sorry, I'm like all over the place here. Okay, so hopefully everyone's following along. So for each, so they tell you this in the problem. For each 2 pi cubed volume in K space, there are 2 electrons. That literally is just saying that these dots, how much space did each of these dots take up here? It's just 2 pi cubed. And of course, there's technically some units that they're just not considering. It's fine. We usually use units where we don't have to worry about the units of K. I guess it should be 1/meters it should be 1/meters cubed, technically. But anyway, and so for each volume in K space, so therefore, if we know the total volume in K space, if we just divide it by this, we'll get and then multiply by 2, we'll get the number of electrons here. Right. Okay. And actually, sorry, maybe it shouldn't be 1/meters cubed. Let's just forget about this for now. But basically, now that we have, and also I'll erase this part for now. Well, forever, I guess. I'm not going to rewrite it. Now that we have this volume, if we say, I'll call this volume total. If we take volume total and divide it by 2 pi cubed, which is the volume for 2 electrons, therefore if we multiply by 2 then we should get the number of electrons in Fermi sphere. Does that make sense? So all I did was take the total volume, divide it by the volume. So this is like volume, well, anyway, this is total volume. This is the volume for 2 electrons. Yeah. So let's just say it's the volume for 1 state. This quantity, this divided by this, would give me the number of states, but we have to multiply the number of states by 2 to get the number of electrons. So you could think of this, and I just wrote the 2 here, but it's really like 2 separate steps, kind of. So, so I could even write V total Well, okay, I don't want to. I was going to put like units so we could keep track of everything, but I don't really want to do that because it's going to be more complicated. But anyway, therefore we get the number of electrons in the Fermi sphere. Let me look something up real quick, actually. Yeah. Okay. And now, well, I guess that's it. Because this is technically in, okay. I think this is it because this is technically in units of meters, 1/meters cubed. The reason I know that is because we have this, and x is in meters cubed. Sorry, no. X is in meters.
Meters.
So k is in inverse meters, and this had a k cubed. So this was an inverse meters cubed, right?
Yeah.
So this should be an inverse meters cubed. That makes sense. I don't want to check with the, but it should work out.
Yeah.
So this should be an inverse meters cubed, and I'm just a little concerned because it seems like this should also be an inverse meters cubed, and then this wouldn't have units. But they say the answer they want is in inverse meters cubed. So it might just be that this is per meter cubed. I'm not positive. I believe that this is just the whole thing, the answer.
Electrons per meter cubed.
Yeah. But then there was another thing where they mentioned that, okay, so this is fine, but now what we want to consider is that when you heat up a metal, it's not like all of the electrons are behaving like in a gas. All of the let's say you had an actual electron gas, like in a cloud in the vacuum. All of the electrons could just get their own excited, like they all have their own velocities. They could all you could dump energy into it, and they would all get their own energies equally distributed. That's the equidistant theorem.
Yeah.
But in this, these electrons, like in the middle, they can't. There's no other. They're all shoved in together. So there's no states they can move to. So they can't have a velocity really, because they have a fixed momentum in the lattice, and they kind of have a fixed position because of the the Azerty principle, and so they kind of can't really move anywhere. And so when you heat it up, when you try to add energy, the only ones that are going to actually do anything different than what they're doing is the ones on the outer shell. So the electrons on the Fermi sphere, so not in it, but on it, will get excited. But that means that you're actually dumping all your energy into not all the electrons, just a fraction of them. And so, actually, can I just see one more? Yeah. Sorry. So, right. Compare this with the volume of K-space and the number of states within kBt of the Fermi energy at room temperature. I see, okay. So they're saying, then they want you to actually do this. And they're saying, when I said on the Fermi sphere, so precisely, I said that roughly, but precisely what it means is that within kBt of sphere. So let me erase that, and I'll erase something, and I'll say what it means. So now we have this answer, and we want to compare it with another. So that's the total. That's if it was a full object. That's actually how many electrons we have, and then we could get a whole bunch of excited electrons. In real life, of course, let me erase this. Let me erase all this, and then I'll say, so we have this sphere, and it's still in K-space. And the electrons within a range, so this is Kf, which is, you could compute, is just corresponds to an EF. So if if an electron has energy what it says is within kT of E Fermi, then it gets excited by adding heat. So if you're at room temperature, they tell you what T is. They say 300 Kelvin or something. So at 300 Kelvin, if you compute this, you'll get a certain energy. So this will give you I'll call this E prime. So then it's E Fermi minus E prime. This is how much energy. This is the energy range we're considering. This is actually, I shouldn't draw it outside. It should really be like from here, E Fermi, to inside here a little bit. So it's only this shell on the outside. It's like a very thin shell with a thickness of this that gets excited. Now, of course, I'm writing energies, and this is in a K diagram, so it's a little bit weird. But like, remember, they're all just related by a formula, so there's no other variables. These are all constants. So this. Let me just make sure. Right. So I think what we want to do is say, what about all the electrons? Actually, hold on. So I guess what we want to find is, so let me write what we want to find. Sorry, E Fermi minus E prime. We want to find number of electrons in shell, percent of electrons. That's what we want. Because they asked something if it's, I think they asked something if it's negligible, or they asked if something small, or how does it compare, or. Let's just pretend that that's what the problem is, because I think that's kind of what they want you to do. I actually think this is probably a better problem then, if that's not what they say, which is just to find the number of electrons in this shell as a percent, meaning as a percent of all the electrons. So then we can see if it's like 50%, then we know that the approximation by assuming it's a gas is like 50% accurate in some sense, or it's like half of. It's kind of like we could assume that we had half the number of electrons we had, right? So I'll just let me just say that again, even though I just want to make sure that's perfectly clear. The assumption that we've made when we did the previous calculation, which we needed to do to find the total number of electrons, which we just did. That's what we just tried to do a second ago. That's saying that all those electrons we counted them, and now we're saying why doesn't a metal with the electrons arranged like this act like a gas with that many electrons in it? Why can't we just assume it's like the equivalent theorem with that many electrons? And now what we're trying to do is say, well, they're just telling us that there's this E prime, which is KT, and they tell us T that we're considering, where only the shell on the outside of the electrons that are participating in this free electron model with the equivalent theorem. So we want to find the percent of electrons that are in that shell compared to the total. And therefore, if we find, again, if it's 99%, then it seems like, okay, we can totally use the equivalent theorem. It's like a free gas, basically, almost 100%. If we find that it's like 1%, that means it's basically like a gas with 1% of the electrons are actual gas molecules and the rest are like not doing anything. So then we'd have to sort of like divide it by 100, I guess, to find, So what we want to do to figure out whether this is a good approximation, which I think the spirit of the question essentially, is to find the percent of electrons in the outer shell. So we already have the electrons in total. That's what we just found. Now we want to find number of electrons in shell. So I think I wrote this and then erased it. But this is what we want. Electrons in, well, we could just say the number of electrons in EF minus E prime amount, right? Because then we could just subtract them to get, we really want to find the shell, but that's obviously harder. So to do that, we can do actually the same exact procedure we just did, but with K Fermi is now it's something slightly different because now K, I'll say K prime will correspond to the slightly smaller radius, K prime is going to be radical 2m EF minus E prime over H bar, right? So it's a slightly smaller Fermi. It's not a Fermi sphere anymore, actually. It's just a slightly smaller sphere. So these are actually all the electrons that are, I won't write it, but all the electrons that are not participating. Then once we do this and plug it back into our formula with the 4/3 pi K prime cubed is the volume again of the sphere, and then we divide it by 2 pi cubed again, we get again the number of electrons in this smaller sphere with this smaller energy thing, and then we could just subtract the original number we got minus this number, and then take the difference and divide it by the total, and we get the percent.
Right.
Right. Does that all
Yeah.
make sense? Okay, and then we literally get the percent, and I'll just give you a small hint, is that it's very small. In case you were, because I gave you all these possibilities, but I don't want to leave you until you do it to find. Also, I just want to, if you get a very large number, it's not correct.
Yeah.
The answer is very small with that at room temperature. Sorry.
Yeah.
Because at 300 Kelvin, that's actually really important. So they tell you it's at 300 Kelvin, which is room temperature. So you think, well, okay, that's everything we're going to do is at room temperature. Mm-hmm. But that's actually not always true, because you can imagine, what if you're in the sun? Does every if you think of the sun as a periodic lattice or whatever, and all the electrons at all points are characterized by this K value in this Fermi sphere, do you think most of them are just kind of sitting there and the edges are? No, it's really hot. So if it's really hot, you'll find that KT is going to be much larger. Therefore, this number is going to be basically, instead of a shell, you're going to get basically the whole sphere again. Once you get hot enough. Once you get hot enough, this difference will become 0. Mm-hmm. Such that the part that doesn't participate is going to be 0. So it's kind of like, here's how I imagine it, is like a cluster of electrons near the center of the Fermi sphere, and then as you heat it up, they kind of start to separate a little bit. But there's some chunk in the middle that don't ever participate in anything. And therefore, the specific heat, of course, is going to change, depending on how many. Of course, if you add more molecules, you have more places to put energy, so the specific heat's going to change. At very, very cold temperatures, you can imagine that all the electrons will kind of want to just not move very much, and only a few will get excited. So your specific heat might actually be really high, really low, really low, because it's easy to change the temperature. I always get it confused, but the specific heat might be low if it's very easy to change the temperature, which might happen when only a few electrons are escaping their Fermi sphere. But and compared to like sort of the world and how many electrons there are, 300 is pretty low as a temperature. So you'll get a very small percent. I think it's close to 1% for most things. 1% of the electrons in a metal will participate in thermal fluctuations at room temperature. So it'll be like you have a gas with 1% of the total electrons acting as a gas and 99% of them sitting in their shell or whatever, their Fermi sphere, Okay.
So this addresses this paradox, basically, that is mentioned.
Yes.
Okay.
Yeah. So the very first few sentences is about why can't you just use the equipartition theorem as it's a gas with electrons in it, right? They're kind of all free. Right. Like we kind of showed that they're roughly free. Maybe they have some weird whatever, but why aren't they all free? And it's just because they can't all occupy the same state. So some of the states naturally have to have a higher momentum, and therefore they're near the edge of the sphere and they're much easier to excite. Mm-hmm. The middle ones don't really have anywhere to go because they're sort of encased, right? Mm-hmm. So anyway. Okay. So that was 11?
Yeah.
Okay.
13th one is 0.5 kg sample of ice with specific heat, 0.5 calories per degree per gram. Mm-hmm. At temperature minus 10 degrees Celsius is heated by adding a constant power of 50 watts. Mm-hmm. How long will it take to get the ice to 0 degrees Celsius? How long will it take at a constant power of 50 watts to melt the ice? And then they give the latent heat of fusion of water at 80 cal per gram. How long will it take to heat the melted ice to 10 degrees Celsius? Specific heat of water is 1 calorie per degree per gram.
So Right.
It's a 0.5 kg sample of ice.
Okay, so there's 4 stages.
Mhm.
So there's minus 10 Celsius, is that right? And then 0 Celsius, and then 0 Celsius for water, and then whatever, was it 10 or something?
Yeah, 10 degrees.
10 again, okay. So this is the stages of what happened. Now I wrote it in 4 because you actually have to do 4 calculations here, right? So if you've done thermodynamics and stuff in chemistry, you know that there's different things are happening here. So to raise the temperature of ice, all you need to know is the specific heat of ice. So if they told you the specific heat in, what is it, calories per degree Celsius per gram?
Cal per degree per gram.
Yeah, okay. So I'll say Kelvin instead of degrees Celsius. It's the same amount. Of course, this number is not the same, but so it's kind of annoying I'm using C, but I'll say Cal. When they tell you the power in watts?
Yeah. It's 50 watts.
That's so stupid. Okay, so so a watt.
Well, we can convert this on Google, right?
You can convert on Google, yes. It's just annoying that you have to do it.
But yeah.
Is a joule per second.
Right.
Mm-hmm.
A calorie is another unit of energy, just like a joule, but it's equal.
Right.
So I would always convert this to joules per Kelvin gram.
Kilogram.
Kilogram. It's kilogram, right?
No, it's gram here, but to convert it.
Oh, that's so annoying. Okay, convert it to joules per Kelvin kilogram, always. Okay.
Mm-hmm.
Or I mean, you could write degrees Celsius if it makes you feel better because these are all in Celsius. It probably looks a little nicer if you do that, but just obviously they're the same. I'll just put degrees Celsius. And so we need to do this because we need to. This is in kilograms, so of course. So once we take this specific heat, or heat capacity, I forgot all the words, but it's the one with mass in it.
Mm-hmm.
You have to multiply that by the mass to get something with joules per degree Celsius.
Mm-hmm.
You immediately always have, and because it's 0.5 kilograms of ice and then it's melting, the whole thing's gonna be 0.5. So we never need to we're gonna need to. It's a different specific heat here, but anyway. So we could multiply it by the mass, this quantity by the mass to get something in joules per degree Celsius. Okay, I would call this the specific heat. But I think technically specific heat is for, this is like specific heat capacity maybe?
That's just heat capacity, and the kilogram one is specific heat capacity.
This is specific heat, and this is heat capacity? Okay. Thank you. I think I was using the words wrong.
Yeah, specific is when you divide it by weight, so it's per kilogram.
Oh, I see. That makes more sense. Yeah, okay. So heat, yeah, okay. So yes, thank you. Okay, I wasn't using it wrong last time. But anyway, this is heat capacity now because it's literally for. Remember, I was saying if you double the amount of water, right, then it's twice as much, right? So this is this thing now. So this does depend on the amount of weight you have, of mass you have. So the heat capacity, but now it's perfect because now we're doing a change in temperature by 10 degrees. So we could just multiply this, so it's a number of joules per degree Celsius. So change in 10 degrees Celsius gives us a requirement of joules. And now if we know the watts in joules per second, we can compute the time it takes. So that's what we need. I think that's what the question asked, right?
Mm-hmm. How long will it take to?
There you go. So once we have, so we start with this given quantity. Sorry, we start with this given quantity. We convert it from stupid units to normal units, and then we multiply it by the change. So then we have a joule. Essentially we're saying how much does it cost for this object? How much energy does it cost to raise the temperature by 10 degrees? That's what this number means. Not this number, but this number. This number would be for a given kilogram of this. Anyway, you see what I mean. So then we could find how many joules it takes, and because we know a constant value of the watts in joules per second, we can compute how many seconds it takes. So that's fine. The same exact thing is going to happen over here, but of course we have a different value for the specific heat and therefore the heat capacity of water. Water does not have the same specific heat as ice does. It does have the same weight because I'm assuming it's just it's the same one, it's the same water. So it's gonna melt. And so this is still 0.5 kilograms. We can still do the same exact procedure, and we can find this temperature here. Now this is the one that's a little weird, because this is called a latent heat. I mean, the heat that is involved in this is called the latent heat of fusion, I think.
Yeah.
For some reason, fusion means melting. I don't know why.
Well, if you think about it the other way, it's solidifying. So
Yeah, but I don't. Yeah, okay, fine.
because it's
Fair
the
enough.
same amount of
Yeah,
heat.
you're right. Okay,
But-
that's fair enough. Yeah, true. Okay, so yeah, it's called latent heat of fusion. The other one's for vaporization if you're turning it into a gas, right? So latent heat would be the amount of heat it takes to take a well, does it? I don't know if does it have kilograms in it. So what do they give you?
80 cal per gram here. So
Yeah, so it's by weight.
80 cal per
gram.
gram. Of course. Per gram. And I notice, of course, there's no degree Celsius because the temperature is not changing, and that's why it's called latent heat. It's literally the whole point. Is the fact that the temperature is not changing is an indicator that this is literally the heat it takes. So this energy is taking ice at zero. So at 0 degrees Celsius, everyone knows, of course, that's the freezing point. But what that literally means is that you can have ice or water at 0 degrees Celsius, right? But those are not the same thing. It's not like those are the same thing, but just one's like a micro degree below. Like it's not continuous, right? It's not like it's not discontinuous is what I mean. It's not like it just sharply, there's a heat involved in taking some liquid and turning it into a crystal structure that makes a solid. And there's something that you lose by breaking all the bonds. I mean, what makes something a solid is that the water forms, the bonds, and it's like whatever. Like it's some kind of hexagon. It probably doesn't even look like this, but whatever. It's a hexagon type thing that you get in ice crystals. And so to arrange those costs you some energy, and to destroy them gets you some energy. Wait, no, that's the other way around.
Yeah, I mean, you destroy it, it'll release some energy. If you destroy the crystal.
Well, the
it
energy is
should
being used
absorb
to
some energy.
energy is being used to break the bonds.
Okay, yeah.
Yes.
Oh, so it should absorb, not release.
Sorry. Yeah, I knew I was saying something. Yeah, energy. Yeah, great. Right. Okay. So energy is being used to break the bonds. Yes.
Yeah.
And then creating those bonds releases the energy.
Mhm.
Yeah.
Right.
Okay. So anyway, so if you want to break those bonds, you'd have to impart some heat onto it. And if you must multiply again, it's 0.5 kilograms. So therefore, you get some number of calories. You convert that to joules. And again, you have joules per second here. So now you can compute a time here. And then you just add up the times and you get the total time to do all these things. The important part of this problem, every problem has like a thing that they're trying to get you to learn. And this one, it's just that you cannot just say that heating water, if they said water goes from 10 degrees to 20 degrees into 30, right? And they said there was a heat applied, that would be really stupid to do, but you could just break it into, like you could not do it all once if you want. You could just say, what's the heat to go from 10 to 20 and then from 20 to 30? Obviously, you're going to see very quickly in the equations, you'll just get an equation that you could have just, you can add them together or you can just multiply it by 2. The delta T in that case. But there is some actual, there is some time it's going to take where you're not increasing the temperature. So if you actually plot if this is time, right, and this is temperature of melting ice that's below 0, so let's say this is 0 Celsius, it will raise some temperature with some slope, and I'm assuming time is sort of a proxy for energy here, right, because it's at a constant power, so, yeah. And then there'll be some amount of time where the temperature is not increasing, because now you're at ice and here you're at water, here you're at some melted ice, but they're both at 0 degrees. Then you will increase temperature again. The slope of this, I don't remember the numbers, but the slope of this is not going to be the same as the slope of this because the specific heat is not the same. Because really what these lines are is a ratio between T and time, which is really energy. Mm-hmm. So remember, temperature versus energy was kind of like how the specific heat was like delta T, right? This is like a slope. Obviously, it's sort of the inverse, but you know what I mean? It's basically a slope of a line of T versus energy. So the higher slope, I guess, would have a lower specific heat or something. Anyway, whatever. So you let's not think about this too much because I'm going to confuse myself. But then you'll get to where it's at 100, where it's boiling, and then you'll have a heat of vaporization, which is the same exact thing. Generally, it's like much, much, much larger for some reason. It's like many, many times. I don't know why. It's like 7 times bigger or something like that. So it'll be much higher, but it'll be at 100 degrees. Then you'll have all water vapor. And then you'll have another specific heat. It'll probably be a higher slope because it has a lower specific heat. Yeah. So anyway,
it's longer because you're vaporizing everything, so gas molecules have a lot more energy than when you
true. Yeah.
solid to liquid.
So right. I guess so. From here to here, you're actually just breaking some crystal bonds.
Yeah.
But you're still having a bunch of intermolecular bonds.
Right.
Here to
gas is kind of a lot of kinetic energy.
here you're breaking all intermolecular bonds. There's no intermolecular bonds here at all. Right. This is pure gas.
Yeah.
So from here to here, it's just a crystal structure. Yeah. So I guess you could think of it like that. I'm sure you could find materials where this would be pretty high because the crystal structure is very intricate or something. Again, I don't. You're figuring out that I don't really know much about this, but this would be vaporization. So this is also latent heat. The reason it's called latent, I should say, is just because it doesn't appear in because you're adding heat and you don't see a change in temperature. So it seems latent just means like a hidden amount of heat. It's not really hidden in any. It's just hidden because you can't see the structure breaking. Really, I guess you can't. I mean, you can. You can see it melting. So I don't know why it's that hidden. But it's hidden in if you just had a thermometer. Because your thermometer in 0-degree ice would read the same as a thermometer in 0-degree water. And the same as this is water vapor. There's a lot of debate. Well, okay, when I was in high school, there was a lot of debate in my class, so this doesn't really mean anything, about whether you should call this steam or not. I think you probably shouldn't call it steam, because steam implies that it's visible. And if it's visible, then it's not water vapor. Because you can't see water vapor. It's completely invisible. But if you see like clouds or you see a pot with things going from it, what you're seeing, if it's white, right, then that's actually droplets of water in the air that are very small, and it makes like a mist, right? And anything you can see is not, like clouds are made of water. They're not made of water vapor at all. You can't see, right? There's water vapor in the air all the time and you can't see it. If it's humid, you can't see anything about the water vapor. Anyway, so some people do call this steam just because it's a nice little word, because it's like ice, it's one ice, water, steam, that'd be a nice thing. But let's just not get into that. Yeah. I would just, to be precise, call it water vapor.
That's interesting because in thermodynamics we use steam tables, not vapor tables, even though
oh, really?
It should be vapor.
So I mean, if they're just defining steam to mean the same thing as vapor, that's fine. I've always heard vapor is unambiguous. It always means a gas thing. Again, if you're talking about clouds and stuff, and you say if clouds are made of steam, I think that's kind of true, I guess. But they're literally made of water or ice, usually, actually. The really highest ones are made of ice. Like actual ice, not like fake gassy ice. It's like literally pieces of ice.
Okay.
Anyway, that's a little off topic. But so, yeah.
I did have a question. You said that steam would, or the gaseous form of water will have lower specific heat?
Yeah.
Yeah. That doesn't make sense to me because won't it have more degrees of freedom compared to water? Or
it should have less because there's no intermolecular.
Oh, yeah. Oh.
Yeah, because all the ones in okay, now I get it wrong. All the ones in water vapor are also in water, plus in water there's intermolecular bonds.
Right.
So energy can go into those too. And I guess this is water really I should be pointing to.
And ice will have the lattice vibrations as well.
Yeah, exactly. So it should have a lower specific heat. I literally always get those confused. Lower because
higher specific heat because you have
higher. Yeah. You're right because there's more places to put the There we go. Higher specific heat because again there's not only do you have I guess it's basically like the vapor that you have all these modes of oscillation, but well, actually, it's not quite. It's probably that's probably true, but I think it's a little more complicated because you actually can't move as well. You can't rotate in ice. You can rotate in all the other ones, right? So you're kind of, I guess you'd have to figure it. It's not as obvious, I think.
Mm-hmm.
You're probably right in just because I think that's true, but it's probably a little harder than just counting because you have to. Yeah, it's probably a little harder than just counting because the vibrations of ice go away when you get to water, but then the rotations in water go away when you get to ice.
Mm-hmm.
So ice is 2.1 kilojoules per kg Kelvin. Water is 4.2, and steam or vapor is 2.
Huh.
And that actually makes sense because water is one of those fluids that has this weird, weird tendency of when you're freezing it, it actually starts expanding.
Yeah,
That's
it
why
has
ice
like
bursts, whereas other liquids, when you freeze them, they contract.
Yeah.
Get closer. So that's why there's this tendency.
I don't remember the diagram, but one of the diagrams.
Triple point of water.
Yeah, I was trying to. Is that P versus T? Is that what they draw, or is it like T versus?
I don't know. I'll look it up, but
P, V, and T are somehow involved in these axes.
Mm-hmm.
Two of those.
Right.
Mm-hmm.
The point is that in almost every other material, you get that when you freeze something, it gets smaller.
I think it's TV.
It makes sense that it would be TV, I guess. Yeah, because
Your volume expands, temperature goes down when you go from water to ice.
so you get this. So this would be ice, water. I think this is right. This would be T versus V. So we haven't gotten here yet. I don't know if we will. We might in the next chapter or something. But there's this weird property that almost every single material has this type of thing, where the liquid is this sort of slope is always like, it's never a negative slope.
Okay.
And what this negative slope just means is that it essentially gives you the fact that ice is actually larger than water. The same amount of kilograms of ice is bigger. So water expands when it freezes. That's the statement.
Yeah.
And so when you decrease the temperature from water, so if you decrease the temperature, if you're in water, you decrease the temperature, you get to ice. Wait a minute.
So that's a different graph. I understand what you're saying. That's for the triple point.
Yes.
The other one is water starts contracting when you lower the temperature until 4 degrees. 4 is the minimum, and then it goes up when you're. So it's V versus T.
Yes.
VT, and you bring it down to 4, and then it goes up sharply when it starts freezing.
How about everyone look that up, because I'm not going to.
Yeah.
I don't want to draw it, but yes, the idea is that that's when they define the density of water, they usually define it like 4 point whatever degrees, because that's the absolute minimum density of water, or sorry, maximum density of water. Yeah. So because below that, as some pretend to have just seen, below that it freezes and gets bigger because the crystals are actually take up a lot of weird space.
Right.
Most of the time they're all closer together, and so that's why the specific heats are a little bit weird. They don't sort of increase or decrease; they kind of jump, because water molecules are actually closer to each other than ice molecules are, which is sort of unusual. But of course, vapor molecules are much farther apart than any of them. So, so they have rotation, they have linear motion. These have rotation and linear motion. And these have lattice vibrations that are, again, a little stranger because they're not just strictly closer. Okay. Yeah. Was that 13?
Yeah, that was 13.
Okay.
14th one is a person makes a drink by pouring 50 grams of water at 20 degrees Celsius over 50 grams of ice, initially at minus 5 degrees Celsius. Assume the glass is well insulated. How much ice is left after the water and ice come to equilibrium at 0 degrees Celsius? How does your answer change if instead of water, the liquid is 50 grams of 60 proof whiskey, which is 30% alcohol?
Right.
So the first part is water and ice.
So the statement that we want to use for this whole thing is that delta Q, which is the change in heat of the system, is 0, meaning it's insulated, right? So if the change in heat is 0, that means that if we calculate, and we have to use this formula. Have you seen this formula before?
Yeah.
MCAT.
Vaguely.
Cat. Anyway.
Yeah.
This is the heat so if you have an object with a specific heat of C with a mass of m, and the change in temperature is this. We actually just used this for the last problem. I just didn't write it all at once.
Oh,
but it's the same exact thing. I called it energy because it is. But this is just heat it's really, I should be calling it heat. I should have said that. But so we have to use this, and cooling water involves it's going to it's going to release some heat. Yeah. Sorry, what am I? So essentially, the equation we want to set up is one where we have Q of water plus Q of ice is going to be equal to Q of final, which if the whole thing, they say how much ice is left or something?
Yeah, how much ice is left after water and ice come to equilibrium?
I see. So okay, so when we know they're at equilibrium
at 0 degrees Celsius.
Exactly, equilibrium when T is 0 degrees Celsius.
Yeah.
And we're essentially finding if we use the mass of the water, the C of the water, and the change in temperature of the water, which is going to be whatever it was originally to 0, which is, so this is going to be that amount in Kelvin. And we're actually going to subtract the heat it takes to melt the ice, right? Because we're going to basically use up some of the heat that we're releasing from the water. Is that right?
Yeah.
We're releasing the heat from the water, and it's going into it's going into the ice. So the ice is actually receiving the heat. I mean, we could also put a negative sign here, but so this is going to be M ice, C ice. Sorry. It's not going to be, this is not right. It's not going to be this because this is for a change in temperature. But if the ice is not going to change temperature, which we know it's not because we know at the end it's going to be 0 degrees because it's ice and it's not cold. Well, originally it was cold. Wait, was it colder than?
The ice?
Yeah.
Yeah, ice is minus 5 degrees Celsius.
Oh, okay, sorry. So it is going to be MCAT.
Yeah.
So it's going to be M ice, C ice, delta T ice. Okay. Plus, then we're going to have some latent heat, right? Which is going to be M, I guess, times
ML, yeah.
ML. That's what they usually, yeah. So L is latent heat per kilogram, and then we multiply with this. So we get this. So this is the total right. And now we want to find, sorry, why am I blanking on this? The heat, we want to find the mass of ice at the end.
Yeah. How much ice is left after the water and ice come to equilibrium at 0 degrees Celsius?
Right.
So there won't be latent heat because we're checking the mass of ice exactly when everything gets to 0, right?
I mean, it says water and ice come to equilibrium.
Oh, okay, sorry.
So some of the ice is melting.
Yes. So they come to an equilibrium. So you know that. So the last thing to probably get to equilibrium would be the water because it has more energy. So we figure out how much energy it takes for the water to get from 10 to 0.
Right, that's this.
Right. Then we take out the energy it'll take for the ice to go from minus 5 to 0.
Yes.
And the rest of the energy that's left, minus those two, would go to the latent heat.
Yes, you're right.
And the mass based on how much ice is converted to water.
I think this is right.
Energy differential would give you the mass conversion.
So essentially we're taking so when Q system is 0, I'm just saying in the individual heats are going to sum to 0, but we're going to put a minus sign here, so it's fine. Or we could subtract this, I guess. Anyway, whatever. Let's pretend I didn't say this. Because then we have to worry about signs. But if we just think about it in terms of the actual, where the energy is in the water, right? The positive energy is in the water. So it's going to, so this is how much energy it's going to contribute to the system, right? The positive energy of the water cooling down is going to give us heat into the system. What's going to take the heat? Well, first of all, the ice that's heating up to zero is going to take the energy by this much, right? Then what's left? Well, the leftover energy is going to be, it has to melt the ice. That's the only thing it can have. Everything's at zero. So the only thing it can have is it melts the ice. So the extra energy that's left over, so this is like leftover energy. And all of it can go into melting the ice. But of course, it's only going to melt. It costs this much energy per kilogram. So this, remember, L is latent heat, which is in joules per kilogram, exactly. So therefore, it costs for each kilogram, it costs you some amount of joules. So if this number is in joules. So if we just say, how much mass could we possibly melt so that all of the energy is used up? We're just setting this equal. We're setting this much energy equal to the energy we actually have left, and there's a certain value for M such that this is used up. That's, really, if I was going to use my original statement, I would subtract this and set it equal to 0.
Yeah.
Which is literally just moving this to the other side. So that's just saying that energy is being contributed by the water. So if I really wanted to write it like delta Q, I'm just doing this because I think in the book he might use it like this. Delta Q equals 0 because it's insulated. So if you wanted to use the fact that it's insulated like explicitly, you would say this equals Q water minus Q ice heat minus Q melt, right? And that has to be 0 because it's insulated. Right. So the energy is being contributed by the water by that much. Energy is being used by the ice to heat up, and it's being used up also by the ice to melt. But of course, this has to all happen because it can't melt without getting to 0. So it has to get to 0, but then it can be melted, but it doesn't have to all melt, right? And we can solve for this M, how much mass it could possibly melt by setting this up. And we know every quantity in here we know except for this M left. It's not the mass of the ice. Because that could just not work, because then we don't have any unknowns. So, right, that would assume that we had exactly as much ice as the water could melt.
Right.
Well, the question is just asking for how much more ice is converted, right?
How much ice is left?
So it'd probably give you the amount of ice before. Because you'll need that for icy ice.
Yeah, how much ice before? It's 50 grams.
Yeah.
Initially.
Okay, good. Yeah, okay. So it tells you the grams and the temperature of the water, has to tell you the grams and the temperature of the ice.
Yeah.
And then, there we go. Okay. And then the second part is about alcohol. Instead of water, it was some percent alcohol.
Yeah, 30% alcohol.
Right. Then it would just be, instead of using M water CW, we would have to use the actual mass of the water CW plus M alcohol C alcohol. But of course, M is not. This is not the same M anymore because, well, if you just add alcohol to it, then sure. But I just mean like if you have 50 grams of whiskey, it's not 50 grams of water, and like it's 30 whatever grams of water and 20 whatever it is.
Yeah.
So you have to. So these are going to be lower numbers, and you multiply each one. You sort of weigh each of them by the specific heat. And I think the specific heat of alcohol is lower than water, because water, as I was saying at the beginning, that water has very high specific heat. Just that's like a rule that it's sort of very high compared to most materials, and so especially most liquids, and so it's going to be a little lower. So it's actually going to be it's going to melt less ice, right? That would be what we'd expect because. Wait.
Alcohol has lesser.
Yes, sorry. Yeah, you're right. Okay, I'm right, and you're all right for nodding at me. Yeah. It is less ice because it melts less ice because we had less heat to begin with, right? A whiskey at 10 degrees or what? Any temperature. Whiskey at any temperature has less heat in it than water at that temperature.
Yeah, it's 20 degrees initially.
Sure. Yeah. So if it's as long as it's at the same temperature, it has less heat in it because it has a lower. As long as C is less than C alpha is less than CW, which I'm assuming.
Yeah.
Then it would have less heat to contribute to the system.
Right.
Therefore, we couldn't melt as much ice, so we would have more left over.
Okay.
And again, it's sort of because whiskey in total has less sort of inertia to resisting its change in temperature. It's more easy to change its temperature.
So here we could consider 30% alcohol as weight by weight, I believe.
Yeah. You do by weight, right? So just take 30% of the mass and, and 70%. All right. Wow, that's excellent timing.
Yeah.
And that's literally the entire homework. Right? That's 14, right?
Yep.
Okay. Wow, look at that.